Hey everybody, welcome back. Today we're going to be doing a lecture on soils and agriculture, the connection between soils and agriculture, and with a strong emphasis on soil structure and its role in plant growth. I think you're going to really enjoy it. Let's just dive right in. Right here at the very beginning is a nice introduction to the whole concept. We have these nice taproot plants. These are carrots living right in the soil. And we're going to be talking about the relationship that exists between the root and the soil itself, the structure, and what conditions make this soil acceptable for, say, a plant like a carrot. Some other plants would not be able to survive in this type of soil. So we're going to talk about the different conditions that might arise as a result of soil structure and plant growth. So in order to talk about this stuff, we've got to get a little vocabulary under our belts. And so we're going to start right off with a definition of what is agriculture. So agriculture is the practice of raising crops and livestock for human use and consumption. So here we see an agricultural field. This is one in Brazil that's growing soybeans. It's entirely grown for human purposes, right? Humans have cultivated this field. They have taken care of the field. They have harvested this field. This is all soybeans, and it's for human use, okay? So that is agriculture. Cropland is land used to raise plants for human use. So this would be cropland in this case that is used in this case for agriculture. Rangeland or pasture are two extremely important and interchangeable terms in a lot of ways. Land used for grazing livestock. So cattle, sheep, goats, things like this. And in terms of how we use the land, we need to be aware of the fact it's a large amount of land we're talking about here. The amount of land that is devoted to agriculture on Earth covers about 38% of Earth's land currently. Now we have to remember the Earth is a water planet. It's 71% ocean. So 29% of the land surface, or the Earth's surface, is land. And of that 29%, 38% of it is used for human purposes of agriculture. And what is it that they're actually doing out there? Is it the plants? Is it the animals? Well, it's actually the soil which is driving people there. So soil is a complex plant supporting system. Consists of disintegrated rock, organic matter, water, gases, nutrients, and microorganisms. And it's a renewable resource that can be depleted if it's abused. So when you think of soil and you think of what's beneath your feet, sometimes we just kind of fall into the fallacy of thinking it's just rock or dirt or there's really nothing exciting down there. It turns out there's a lot going on beneath your feet, and we're going to spend some time digging through that. And one last term that we need to bring up before we move on here is sustainable agriculture. So sustainable agriculture is agriculture we can practice in the same way and same place far into the future, right? So it's a type of agriculture. And one of the things we're going to learn by the end of, I would say, the next lecture or two, we're going to learn that while this is wonderful, lots of soybeans are coming out of this field in Brazil, it's not particularly sustainable. Okay, this is something we could do for a while, but it is having effects. And so we're going to talk about that going forward. All right, let's jump into it. So the reason why we're going to focus so strongly on soil when we get into our agricultural portions, our agricultural lectures going forward, is because soil is the base. It's what supports all agriculture. So agriculture and plants require healthy soil to, one, provide nutrients, and two, have a structure that allows roots to penetrate deeply, and three, to retain water. So those are three important features. And I'm going to direct your attention to this photograph over here to the side, where we have a cutaway of soil with a plant, and we can see that this plant has about half of its mass is probably underground, maybe even more, right? Because we're only seeing this in 2 dimensions. So this plant is growing into the soil. It almost has like a spider web type structure moving through here. And then it turns out about half of this is sticking up above, and there's the leaves, and the leaves are undergoing photosynthesis. So here we see the energy accumulation and the chemical storage through glucose. And then down here we see a totally different thing happening. So what we see is that we have this black soil that it's built up around the root structures here. And it turns out that black or brown color is usually organic matter. So organic matter provides nutrients and helps with structure and water retention. It turns out the organic matter prevents the water from flushing down through the soil too easily, but it also keeps it from waterlogging or flooding the soil at the same time. So it's a very good mediator of water. And it turns out it's a big deal. Soils that retain water make the right amount accessible to plants. You don't want to drown the plant. And of course, you don't want the plant to dry out. So you have to have enough constantly in reserve, and soils are actually really good at doing that. Now, nutrients such as nitrogen and phosphorus enable plant growth, and those are also derived from the soil. Nutrients, in particular nitrogen, is derived through the nitrogen cycle, which comes from the atmosphere through a complicated series of nitrogen-fixing reactions that wind up allowing the soil roots to be able to take it up. Whereas phosphorus is generally consumed from dead organisms that have died and are being decomposed. And it also can be derived from the rock cycle from which the soil itself is derived from. We're going to get into the origins of soil here in a couple of slides, so hang on for that. So soil structure and texture influence root penetration and growth. If you have soils that are too hard, the roots won't penetrate and the plant won't grow. If it's too soft, the roots won't have anything to hold on to. Then the plant will be removed or damaged very easily by wind or some type of surface feature. Okay, so it has to have the right texture for the roots to be able to hold that particular plant in place. So you need to have the right roots. The roots have to match the soil. The roots have to match the amount of water. The nutrients have to be right. The amount of organic matter needs to be right. You can start to see pretty quickly that there's certain plants that live in certain kinds of soils around the world. So that's what we're seeing here in this image. Livestock depend on healthy soil because they depend on the plants that grow there. That's kind of common sense. It's the next step, right? If you want to have healthy livestock, you need to have healthy soils to grow the grasses that they survive off of. And then, of course, soils have sustained agriculture for thousands of years. And it's our plan to create a sustainable system that's going to continue to do this forever. Nature actually makes very sustainable soils automatically. Human beings, through their interventions in soils and with our machines and so on and so forth, tend to degrade the soil. And so our next lecture, it won't be in this one, but our next lecture will actually deal with that very issue. So let's talk about where agriculture came from. Turns out different cultures independently invented agriculture. If we look at a map of the earth right here, we notice that there's orange zones and yellow zones. The orange zones are centers of origin of food production. So this is where human beings came together and developed agriculture based upon the plants that reside in that area. One of the primary places this happened, or actually I should say the first place this happened, is probably the Fertile Crescent or in Mesopotamia. This is based upon archaeology. About 10,000 years ago, we have very good evidence that human beings were coming in and they were doing agriculture, which is planting crops. Okay. Shortly thereafter, we have very good evidence that this was happening in China, New Guinea, Ethiopia, West Africa, the Andes Mountains, and Mesoamerica, as well as in the eastern United States. So these are places that independently developed the origins of food production. Now, the yellow zones show us where food is grown today. And they don't necessarily always coincide. For example, in South America, the great food growing region of Argentina and Brazil does not match where we see it up here in the northern portion of the Amazonian rainforest, okay, or in the up in the Andes. The same thing is true of course, in Africa, and where we see tremendous amounts of production of a lot of things that were from the Middle East, as well as from Africa, grown in Europe. Same thing in India. Okay, China and the eastern United States are two exceptions to this, where we actually see the food being grown still heavily in the very areas where it was developed, here and here. All right, so it turns out that raising crops produces a positive feedback cycle. So let's go over that cycle. So you're harvesting the crops, which required people to be sedentary. In other words, if you're growing a whole field full of something, you can't be moving around. You're going to be there, you're going to be taking care of it and making sure things don't get into it. So you're going to be tending that field. So that makes you sedentary. It means you're not moving around. You got time to do other things, perhaps. Being sedentary, of course, encouraged the planting of more crops and production of more food. So if you're going to be there anyway, you might as well just plant larger fields, even more than what you would consume. So it's an overproduction that might happen. And these more crops allowed larger populations, and then larger populations required planting more crops. And there's your positive feedback cycle right there. Okay, and very shortly thereafter that you start seeing the development of cities. Cities are areas where people are generally sedentary. They're not moving around. They're not traveling hundreds of miles following buffalo or deer or something else that might be hunted. In this case, they're staying somewhere nearby, and they're engaging in something that would develop into an economy, something called a market economy, in fact. We'll get to that here in a moment. So it turns out that agriculture from the very beginnings has evolved a lot. But most of that evolution is pretty recent. Traditional agriculture is a very basic system. Most of us would recognize it. Some of us even have great-grandparents that described having to work in some of these environments of what we call traditional agriculture. And this is where we are talking about biologically powered forms of agriculture that use human and animal muscle power to make everything happen. So that means you're using an ox or a horse to maybe pull a plow. You might be using hand tools like a hoe or a rake. Simple machines might have been implemented at the time. And in fact, we see in very ancient art, this is actually from a tomb in Egypt from the 15th century BC, we see things that we recognize that farmers would be doing as recently as 200 years ago, right? So here we see, this would be the harvesting or threshing of wheat, the storing of wheat. So this is a grain store that we see here. We see digging and tree cutting that's happening over here. We clearly see a domesticated animal that's doing some plowing. And these are things that happened right up, like I said, right up into the 1850s, 1860s. And a lot of that was replaced by tractors and machinery later on. But we recognize that this is something that was pretty standard worldwide everywhere you go. And this is, in here we're actually seeing it on a piece of art in a tomb in 15th century BC Egypt. Now, what was going on back then is something called subsistence agriculture, which is a form of agriculture in which families produce only enough food for themselves. So they would have a local farm and they would grow what they needed. And on that farm would be numerous crops. Some of different amounts depending on the demand for that family of a crop. And so they would develop something called a polyculture, which is different crops that are planted in one field. So you might have an area where you're growing, I don't know, pumpkins and corn, whatever it is, watermelon. You could think of whatever it is that you're growing or what your desire is, and you would grow that in your field, and then you would live off that. So that's your subsistence agriculture. You don't need any money. All you need to do is be able to go into the field and pick what you needed, and you needed to be careful with how you stored that material to make sure that you got through the winter or whatever it is that you were planting those crops for. Now, market economies came along a little bit later, and it changed things considerably. So market economies allowed, oops, my pen's not working here. Here we got it. Market economies allowed farmers to sell their product. So in other words, they could sell their corn and get coin in response, right? So you can't eat a coin, but you can trade it for future needs, future goods and services. So you didn't have to use it all at that moment. So what that allowed people to do was to overproduce and to keep the difference in in the form of coin. So this also, in order to do this, of course, it increased the use of irrigation and fertilizer, and we started to see a strong desire to have a large amount of agriculture because you can produce a large amount of income by doing this. And this happened for a very long time. Since about the 1850s, right up into, especially into the 1920s, we see a very rapid transformation where we go from traditional agriculture into industrialized agriculture. And that's what dominates to this very day. So industrialized agriculture is a form of agriculture that uses large-scale mechanization and fossil fuels to boost yields. So here we see a farmer. This is on a old corn picker and a trailer. This is actually pretty outdated stuff today. Most large companies that are out harvesting corn would use a very different type of corn picking device. But anyways, you can see that even with this older equipment, he's much better off than the old traditional subsistence farmers were, who would come out with their hands and pick the corn. This machine is doing it for him. What would happen here is he would put fuel into his tractor, so it's going to use fossil fuels to make this happen, but he and that tractor can do the work of many, many, many other workers. And so what that does is that liberalizes a lot of people, so they don't have to go into the farm and work. There's a lot of other things that they could do with their labor, and so they went on and did other things. It made it so that fewer people could produce just as much or sometimes even more food than was happening before. So that's one of the advantages of industrialized agriculture. But in order to make this field happen, you need a large amount of pesticides, you need irrigation, you need fertilizers, and usually it's done using monoculture. So monoculture is a uniform planting of a single crop. So in this image here where the farmer's working, this is all corn as far as the eye can see. He's probably using some type of herbicide to keep weeds out of here, and the only thing that's growing out here is effectively corn. And why does he want to do this? Well, because it's really easy to harvest, right? If you invest in machinery that only harvests corn, that's the only thing you want out in your field. So there's a strong financial incentive to make that happen. Now, a lot of this really took off after about World War II during a period of time called the Green Revolution. So during the Green Revolution, new technology, crop varieties, and farming practices were introduced to developing countries. And what this did was it increased yields and decreased starvation. And you would say that's perfectly great, right? We don't want people starving, but it does come at a price, this style. And we're going to talk about what the Green Revolution brought about in a little bit. But it degraded the integrity of the soil over time, and it is still having that effect. And we're going to talk about how that happens over the next couple of videos. All right, so the basis for all of this is the soil, right? So you can't grow corn without the soil. You can't grow wheat without the soil. You can't even grow a polyculture without the soil. So we need to talk about what the soil is and get into how the system that is soil works. So soil is 50% mineral matter, and it's up to 5% organic matter. It consists of dead and living microorganisms, decaying material from plants and animals, and it's all kind of in a single coherent block working together. The remainder of that space, which is about 45%, is pore space taken up by air and water. We don't necessarily always think about how much open space is beneath our feet, but those openings beneath our feet allow insect penetration, root penetration, water penetration, gas penetration. It's all beneath you. And if you're able to get those things cycling around, remember, those are the 4 biospheres. Your minerals are part of the geosphere, the biosphere, the hydrosphere, and the atmosphere are all coming together in that soil. And so you're going to have a vibrant ecosystem down there. And so it turns out that soil is teeming with bacteria, algae, fungi, and protists, and provides habitat for earthworms, insects, mammals, reptiles, and amphibians. It's incredible what we'll find down there. Here we see in this block diagram here, earthworms, bacteria, springtail, and a nematode, protozoa. And of course, as insects slide through the soil, they have little biofilms on them that makes them feel slippery, but it helps them work their way through this soil matter. Okay. Now, since soil is composed of interacting living and non-living matter, it is considered an ecosystem. Okay. All right, so in order to really understand soils, we have to understand where it comes from. So one of the ways that we're going to argue about the structure of soil and how it should operate properly with plants is to know where it comes from, what its origins are. And it turns out that it's pretty straightforward. It makes sense. But you got to follow it through carefully. So let's go ahead and build this case on where it comes from. First off, it comes through time, so it forms slowly. And it's a combination of time and parent material. So parent material is the base geologic material of soil. And it could be lava, it could be old volcanic ash, it could be rock of any kind. It could be sand dunes, for example. And it also could be derived from bedrock, which is the solid rock comprising the Earth's crust. This is stuff down deep below us. It's crystalline, it's hard, it's involved in tectonics, and that bedrock is very much playing a role in the kinds of soils that are going to form on top of it. So we take parent material, combine that with time, and we have to add one more, or actually 2 more elements. The next element is weathering. So weathering is a process. that happens at the Earth's surface. And this process occurs in several ways. It's processes that break down large rock particles down into smaller ones. So when we think of a soil, we think of that mineral matter, we know that it came from something that was cohesive and large at some point in the past, but it's all broken down now. Okay, and it can happen in three different ways. There can be a physical way of weathering things down, something called physical or mechanical. It's usually wind or rain beating up on the material over a very long period of time. It turns out water is extremely effective at breaking down material physically. Okay, another way is chemical weathering. So chemical weathering is pretty impressive in what it can do. It turns out that rainwater that falls out of the sky has a pH of about 5.5. The reason why it has a pH of about 5.5 is there's a little bit of carbon dioxide in the atmosphere at all times, and it combines with water, and it forms carbonic acid. So you get a little bit of carbonic acid blended in with rainwater that moves the pH to 5.5. So you're basically dousing all the landscape in slightly, well, it's not just slightly, it's acidic rainwater for millions of years. And of course, if you do that long enough, even on rocks, even something like a granite, you're going to see pretty dramatic chemical changes to that rock. And one of the results is you start to form, you start to break down this rock, and it gives the material that you need to form soil. Another way that we can form or cause weathering is biological. Simply having organisms that are physically running through the soil or running through the rock, little roots from trees coming in and breaking the rock material up. So that's what I mean by biological. All of those processes together will take large rocks over time and smash them into smaller and smaller pieces. So smaller than sand, it'll get down to something called silt or even clay in some cases. Another process or another thing that is formed right alongside the weathering cycle is humus. So humus is spongy material formed by partial decomposition of organic matter, and it holds moisture. So here we see a bunch of that humus right here. There's a plant growing out of it, but that black material, that organic, rich, wonderful material that holds all the good stuff that we need for plant growth is going to be in that humus. And so the decomposition mixed with the weathering and good time and a good parent material will give you a set of soils in which certain plants can grow. All right, so let's talk about some of these key processes, because it turns out when you go to one location, the soils are very different than they are in a different location. And it's because of the combination of those things. But it's not just simply the combination of those things. It turns out there's a couple of other influencing factors. So we got weathering and accumulation and transformation of organic matter. We just talked about that in the previous slide. They are influenced by the following factors. So climate is a big deal here. So soils form faster in warm, wet climates. So here we see a desert. This is an African desert, and in African deserts, they tend to not be so wet. And because they're not so wet, they don't get the type of climate where you find very rapid formation of soils. So when we look out here, we don't see the traditional soils where we got plant supporting material. While there's plants out here, you don't have huge accumulations of it. Whereas in a tropical rainforest, where it tends to be warm and wet at the same time, you get trees all over the place, very, very vibrant ecosystems that are set up. And here there's an ecosystem, but it's very, very thin and very, very fragile. Okay. The organisms play a role. Plants and decomposers add organic matter. If the decomposers aren't there, you don't get the humus. And if you don't get the humus, you don't get the soil formations that's plant supporting. Topography plays a big role. This is the way that the hills roll up and down. So hills and valleys affect exposure to the sun, wind, and water, which of course the sun gives you the energy. The wind is going to give you that weathering, and so is that water is going to give you both the physical and the chemical weathering components. The parent material also is going to affect it. You're going to get a different kind of soil if it's from limestone versus if it's from granite or sandstone or something like this. It all is coming to pass. It's kind of a really complicated story behind almost every single soil. And of course, time. Soil can take decades to millennia to form. It's an extremely interesting field to study. It's complicated. The number of soils that exist on Earth are in the tens of thousands. And we are constantly classifying new soils all the time. And it's all based upon all these different criteria. Okay, so I just want to let you know that this is a huge field, and in no way, shape, or form are we going to cover any of it. What we're going to do is we're going to tackle this from a very simplistic viewpoint, right? This is kind of a prototypical or typical soil. It depends on where you live, but it can be pretty typical of soil formation in most places on Earth. That's what we're going to focus on. So when we look at soil, we usually imagine just the stuff up here at the top. So here we actually have a cutaway of an imaginary earth where we got a tree with the roots coming in. And we usually think about that black or brown material up at the very surface, okay? But it turns out when we go below it, there's layers down below. And those layers aren't called layers when we're talking about when we're talking about soils. In sedimentology, we talk about layers, but when we're talking about soils, we talk about things called horizons. So a horizon is each layer of soil. So here we have a layer, here we have a layer, here, here. And then this is actually the unweathered original parent material bedrock. We wouldn't call that a layer, but we frequently call it the R horizon, R standing for rock, okay? So soils can have up to 6 horizons. It's pretty impressive how much difference exists between each one of these horizons. And they're all part of the same system. So where does that come from? Okay, well, we're going to get into that here in a moment. We got to go over some processes and a little bit of definition right now. So a soil profile is the cross section of the soil as a whole. So here we see a profile of a soil, okay, with the material, the brown material up on top, and it's going to change color pretty dramatically as we go down through that profile down to the rock. Okay, and this is a result of the degree of weathering and amount of organic matter that decrease in lower horizons. So we got a lot of organic material up here on top, not so much down here, and that's going to have a chemical difference or chemical effect that's going to result in these differences. Another process is leaching. So this is a process whereby dissolved particles move down through the horizons and may end up in drinking water. So constantly it's raining up here. You might be watering this field. Imagine this is an apple tree or an apple field or something. So you're out here irrigating. That water is constantly running through that soil from the surface down to the bedrock, okay? And as it moves, it has the ability to remove particles, dissolve those things, and to move them from the top down lower in the soil, okay? So some materials, it turns out, in drinking water are hazardous, and this is pretty common in countries like Bangladesh, where there's a type of mineral that exists called arsenopyrite. That arsenopyrite, if it's interacting with oxygen in the atmosphere through complicated groundwater processes, that arsenopyrite can release arsenic into the water, and that can get leached out of the rock and out of the minerals and into the groundwater, and that can cause some pretty serious health hazards. Another thing we need to bring up is this concept of topsoil. Topsoil is the really crucial resource for plant growth that we're really going to focus on in this lecture. So topsoil is the inorganic and organic material most nutritive for plants, and it's vital for agriculture. And so when we think of topsoil, we're really talking about the A horizon up here. So we haven't got into what these are here, but we're going to get into them here in a moment. But we have the A horizon, the B horizon, and the C horizon. And occasionally we have a couple of extra horizons in there that might show up under special conditions. If we have good plant growth and a lot of leaf litter and dead things that are on the surface, we might create an O horizon way up here on the top, the O standing for organic, okay? So this is the loose and partly decayed organic matter. And then right below that is the A horizon, which is where we have the mineral matter mixed with some humus, okay? And then down below we have the B horizon. This is where we see some pretty interesting effects that actually usually stain this an orange or a pink in some cases relative to the A horizon, even though it's made out of largely the same stuff. We're going to get into where these come from over the next couple of slides. First thing I want to focus on is the O horizon. So in the O horizon, there's no mineral matter. It's only made up of leaf litter and organic material. And so here we have a soil core that has been removed, and it shows the O horizon of a type of soil called a spodosol. Don't worry about what a spodosol is, just focus on the fact that when we look at this here, we see no mineral material in here. We've got leaves, decaying twigs, probably some dead bugs, things like this in there. Now, decaying organic matter creates humic and fulvic acid in that layer, which are very important for plant growth, it turns out. But remember, we're already raining acid down through rainwater, which is a pH of 5.5. It interacts with that dead and decaying material at the surface, and then we're creating fulvic and humic acid, which, while important for plant growth, also is going to have important chemical effects going down through the soil. The next layer down is the A horizon. So the A horizon is a layer of mineral soil. So this is where we get minerals. Remember, the O had no minerals. So now we have minerals with most organic matter accumulation and soil life happening in this layer. So this is where the action is, right? This is the really rich, good stuff that we use to grow plants in. Additionally, due to weathering, oxides, mainly iron oxide. Now, if you think of what iron oxide is basically rust, right? It's a form of rust, depending on the level of oxidation and so on and so forth. And it's kind of a complicated little process. But these oxides are usually an orange or a pink or a red color. And so these things tend to form, and they could be accumulated, or they could actually be leached out, right? They can be passed down. And it usually has a pronounced soil structure. So let's go ahead and look at an image here. This is a cutaway of a profile showing the A, B, and C horizon. So here's the A horizon. The A horizon's got a mixture of that nice, beautiful organic material that's coming in from the very thin O horizon up here at the top. You can see where the roots are and things are dying up here. This seems to be somebody's yard or field or something like this. So the O horizon is quite thin. But here's the A, right where this arrow is. And here we've got mineral material, we've got open spaces, we've got little divots in here, which is probably where earthworms and roots were in the past. So it's a very active and vibrant system. Okay. Sometimes when we get a tremendous amount of, I should say, dissolution of certain materials, you can, and clay minerals, you can move these things, you can dissolve them and move them downward. So here we see the surface, here's the old O horizon, this is in a different soil, here's the A, and what happens is you can get intense leaching that will happen, right? So let's go ahead and read this. In some soils, clay minerals, iron, aluminum, organic compounds, and other constituents are soluble and move downwards. So water comes in, it's leaching this stuff out, it's moving it downwards. When this eluviation, this is that leaching and transport is what that means. Okay, when that happens, a lighter colored E subsurface soil horizon is apparent at the base of the A horizon. So here we see it, right? It's highly leached. It's a nice, beautiful white band right here in the middle between these two black sections right here. Okay, so what we see here is a nice E horizon, and it exists as part of the A. It's the base of the A horizon, okay, or near the base of the A. And so here we have the A horizon, and here we have the E horizon, okay. E stands for eluviated. This is a zone of transport away, right? So materials are leaving that zone of the base of the E base of the A horizon, which forms the E, okay. So the next layer is going to be, as we move down, we got O, A, E. Now we're going to head into B. Okay, so this is going to take us back to our previous picture. It's commonly referred to as subsoil. The B horizon can also accumulate minerals and organic matter that are migrating downward from the A and E horizons. If so, this layer is known as the illuviated or illuvial horizon. Okay, so this is a zone of accumulation. Well, what is it accumulating? It's accumulating a lot of the clay, it's accumulating a lot of the iron oxides, it's accumulating a lot of the aluminum oxides. When that happens, we get a zone that tends to be kind of pink because you got the iron. The iron tends to stain the soil. So here we don't have a pronounced E, but we have a clear A up on top. So we've got A, and here's our B. And then down below we have a little different texture. It's a different type of material. It turns out that is our next horizon, the C horizon. In this case, it looks like it's derived from sand dunes, but the sea horizon is usually stuff that is very similar to the original parent material. Okay, it can contain material as large as boulders and cobbles in it. This looks like it's sand dunes or something like this. I actually am not familiar with what the material is here in the sea horizon on this particular image, but here you can clearly see all three, A, B, and then down here is C. Okay, and this is the original parent material with the soil forming on top. All right, so we've got to talk about R horizons. If we've talked about C, we might as well go all the way to R. So R horizons denote the layer of partially weathered or unweathered bedrock at the base of the soil profile. So here we have a soil profile here, cut right into this cliff face. Unlike the above layers, R horizons largely comprise continuous masses of hard rock that cannot be excavated by hand. So here we see that hard rock down here. It's strong. This is something that is not soil at this point. It can, if it's exposed to weathering long enough and broken up, it can become soil. On top of that, though, if we look carefully, we can see that there's gravels and cobbles in here. And this is that sea horizon right here, where we see it's broken up. And then presumably, if we got up here onto the top, we'd actually start to see the B, possibly an E and an A and an O horizon right up to the top of that cliff face. But this is a clear R horizon right here. Okay. All right, to figure out another important parameter of soils, or to classify soils, is to understand its color and its texture and what those things mean, and as well as the structure and the pH. So those are four important things. So let's talk about soil a little bit. So soil color indicates its composition and its fertility. So if it's black or dark brown soil, it usually means it's pretty rich in organic matter. And it means it's probably going to be pretty easy to grow stuff in. If it's pale gray or white soil, it usually indicates it's pretty leached or pretty organic poor. All right. So usually you would take, if you just happen to have white soils in your yard and you're trying to grow things and things aren't growing well, try using something with a little humus in it to kind of pump up the fertility of that soil. Soil texture is determined by the size of the particles. So it turns out there's three main particle sizes that we're going to be concerned about for soils: the clays, the silts, and the sands. So the smallest is clay, the middle is silt, and the largest is sand. And there's kind of an easy way to figure out the difference between the three of them if you're ever making an estimate in your backyard. There's actually easier way. There's more direct ways. I shouldn't say necessarily easier, but there's direct ways of doing this. But clay, you can always detect as different from silt and sand by their texture and by their look. So sand, you can feel and see. You can see the individual grains. You can take a little bit of sand, put it in the palm of your hand, and you can actually play with individual grains, and you can see them. Silt, on the other hand, is so fine that the human eye has very, very strong, has a lot of difficulty identifying a single grain, but you can feel it with your finger. So it's kind of this weird zone where you can feel it, but you can't see it. That's silt. And then clay is where you can't see it and you can't feel it. It's just too tiny, but you can feel its texture. It's usually sticky. It might make your skin feel a little dry. That's clay that's making that happen. Okay, so clay you can't see and you can't feel an individual grain. Silt, you can feel the grain, but you can't see it. Sand, you can see it and you can feel it. Okay, so those are the three different things. And it turns out that the stuff that really grows well, or really kind of has the stuff for planting or for plants to grow well in, are loams. So loam is a soil with an even mixture of the three. So that means you've got large sand, which allows good drainage, but it also has clay in it, which allows some adhesive or some protection against the water just dropping right out of it. So you want a blend of these things. Of course, it affects also how easily air and water travel through the soil. If you have a large amount of clay, it turns out, water and air get through it very slowly. It's very difficult for these components to get through the soil. If it's got too much sand, it has difficulty holding water, right? But the water will go through it very easily. So how that happens is pretty complicated. And so that can have an effect on the kinds of plants that you can grow in that kind of soil. Okay, influences how easy soil is to cultivate, of course, as well. Now let's use an example, 30% sand, 50% silt, and 20% clay. If we go out and we do a test and we find out that that's how much, or what the percentages are in a soil sample, we can classify that. We want to know if it's a loam or if it's a clay or a sand or whatever. And the way that we do that is we can plot it on this chart. So this is a ternary plot over here. Ternary plot is unlike your regular XY axis. It actually has 3 different ends. And so each one of these corners of this triangle is referred to as an apex. So here's an apex for sand. So this is the sand percentage as we go this way. 100% sand is at this apex, and we call that sand. If we go to this apex, you notice it increases in numbers, and here we get to clay. So that's 100% clay up here. And then silt is 100% over here at this apex. You can see we call it silt, clay, and sand for that very reason. So let's imagine we come back to our hypothetical sample, 30% sand, 50% silt, and 20% clay. Well, the first thing we can plot, of course, is the sand. So the sand is right here, and you see I just drew the line here. So we come up to here, here's 30%, we draw that line, and it's 30% away from sand, okay? Then we put on the next line. The next line is 50% silt. So here's our silt line, here's 50, and we just draw our line down from 50 to 50 right here. And of course our last one you can almost kind of see right away is going to be, here's our silt apex over here. So here's the 20% on silt, or I'm sorry, on clay. Sorry, I misspoke. Here's our clay apex over here, 20%. So this is going to be this line right here. And so let's go ahead and draw that. And we'll see that it all comes through and it plots at this point right here. What's really cool about this actually is that you don't really need all 3. You can see where the 2 cross, where the sand and the silt crossed, is also the same place where the clay came through. But we have a pretty good way to classify this, and a soil that has that composition would either be a loam or a silt loam. It's right on the border, it turns out, between the 2. But that's actually pretty good growing soil. All right, another thing that we need to be concerned about is soil structure, which is to say its measure of soil's clumpiness, which is to say how it's cohesive, how it holds together. So a medium amount of clumpiness is best for plants. Repeated tilling, it turns out, compacts the soil. It's actually not good to constantly till the ground. It hardens, especially down about 18 inches down, because you're running a tractor over it all the time. So you got to be very careful. And of course, if you compact it, that decreases its water absorbing capabilities. We need to talk about soil pH too. So we got clumpiness, and the last one is soil pH. So soil pH affects a soil's ability to support plant growth. So soils that are too acidic or basic can kill plants. We're going to get into why that is here in a moment. Okay, but pH, it turns out, influences the availability of nutrients for plants. Let's talk about why. The main reason why is because of a process called cation exchange. So cation exchange is how plants go and get the nutrients that it needs for survival. So imagine we have a soil, right? So a negatively charged soil is going to be holding cations, right? So cations, if we remember from our energy and matter lecture, cations are positively charged. So if you have a negatively charged soil, it'll hold those cations. What kind of cations might the plant need? Calcium, magnesium, and potassium are pretty common, as well as possible iron and things like this. So it needs these cations. They're already in the soil. The soil is going to hold on to them because the soil's got a slight negative charge. Now what the roots do is something very interesting, is they donate hydrogen to soil in exchange for these nutrients. So in the plant world, in interacting with soil, hydrogen is almost like currency. And the roots are able to come in and trade. They push in the hydrogen. Remember, hydrogen is basically a proton. It's a positive charge. And what it does is it forces a proton in, and what that does is cause the soil to regurgitate back a cation, which is also positively charged. So it's a trade that's happening here. And in order for that to happen, you have to have the ability to accept those hydrogens from the roots. So that leads us to an important concept called the cation exchange capacity. This is a soil's ability to hold cations. So cations that don't leach are more available to plants. if they're not washed out all the time. So that's actually where a lot of the humic and fulvic acid comes in. It helps prevent a lot of these things from moving out, and it holds it within the soil structure. It's also a useful measure of soil fertility. So it's greatest in fine textured or richly organic soils, but the cation exchange capacity decreases with lower pH. And the reason why that happens is, if you remember, the lower the pH, that means the more protons or the more hydrogen is already present in that material. So if a plant is already coming into the soil and the soil's got a very low pH, which means it has a large number of hydrogens, it doesn't necessarily want to do that exchange because it's already saturated or has plenty of hydrogen already. So it's not going to allow that to happen. So very acidic soils, it turns out, will have very low fertility because they have a very low cation exchange capacity. I want to quickly mention some soil structures, alternative soil structure, because it's a really big deal when we start looking, especially at tropical rainforests. So soil characteristics tend to change no matter where you are. The rainforest is a big deal. So in rainforests, the nutrients are in plants, not the soil. There's very, very little in the profile for an A horizon. The A horizons are usually very thin, and sometimes they're non-existent. All you have is an O sitting on top of a B horizon with a C. And let's look at this hypothetical soil profile that we have here. Here we have a soil profile where the O horizon is like 2 inches, maybe an additional 8 inches of A horizon in this hypothetical one, and then we go down into the B, and then we go into C. By the time we get to the B, we're about 30 inches down, which isn't far. So we can look at this cutaway that we see here of a tropical rainforest, and we'll notice that pretty much everything is happening right along that edge. All the trees, everything, all that life is happening right there at the top, right there in the O horizon. There's almost no A horizon at all. There might not be one at all. And then here we see that orange, very, very illuviated B horizon, right? This is a zone of accumulation of those iron oxides over very long periods of time. It's turned it into a red soil that is actually not very fertile. Okay, so rain will leach the minerals and nutrients, reducing the accessibility to roots, and rapid decomposition of leaf litter results in a thin topsoil layer with little humus. So this is where the whole action happens. And so if you do any damage to that upper couple of inches, you can damage this whole thing for a very long period of time. And so this is what we see for a soil profile from a typical tropical rainforest in the Amazon, for example. All right, so we're about finished with this lecture, but what I want you to do is look into the comment section down below, and you'll notice that I have a link to an amazing video put together by Dr. Friedland. You're going to like it. It's where he and a graduate student go out and actually look at a soil profile. It's amazing. It's a beautiful spotosol, and I highly recommend that you do it as soon as you finish this video. All right, so with that said, we'll see you in the very next video where we talk about soil conservation and techniques for basically dealing with the loss of the topsoil and the abuse that it's suffering across the world. All right, catch you in that video. Take care.